Hello. In part one of our intro to polynomial functions, we defined polynomial functions. We looked at examples and non-examples, and then we looked at the degrees and leading coefficients of polynomial functions and came up with the general end behavior for each of those types of functions. On this video, we're going to look at actually graphing polynomial functions. First, we're going to make sure we can determine and find zeros of polynomial functions. And in order to do that, we need to be able to factor. So we're going to do a little Are You Ready section where we factor each of the following of these polynomials. When we factor these polynomials, what we want to do is we want to pull out the largest term and then factor the parts that remain as well if possible. So looking at example A, I have 5x to the fourth minus 40x to the third plus 35x to the second. So the biggest x term that they all share that I could pull out is an x squared. And then each of their coefficients is a multiple of 5, so I could pull out a 5x squared. Essentially, then we are dividing each of these terms by 5x squared, which will remain or which will result in an x squared minus 8x and a plus 7. So if I divide 5x to the fourth by 5x squared, I'm left with x squared. If I divide negative 40x to the third by 5x squared, I'm left with negative 8x, and so forth and so on. But guess what? I can actually factor this trinomial because I can find two numbers that multiply to get positive 7 and add to get negative 8. The numbers that multiply to get positive 7 and add to negative 8 would be negative 1 and negative 7. So I can split this trinomial up into its factors of x minus 1, x minus 7. If I were to multiply that out, I would get this, okay? And so this is now fully factored. Again, factoring is being able to break something down that you might have expanded all the way out. Okay, so being able to break things down and build things back up is a very important skill in math class in general. All right, looking at part B, we have 30x to the third minus 35x squared minus 24x plus 28. Okay, now this one's a little bit funky because we can actually factor this by grouping. If you look here, both of these share a factor of 5 for their coefficients, and the highest factor that they share is an x squared. If I divide that out, I'll remain with a 6x minus 7. And then here, I can factor out from each of those a negative 4, because 4 goes into 24 and 4 goes into 28, and if I take out the negative, that's going to remain a 6x minus 7. And so now they share these two terms, so I can actually factor out the 6x minus 7, and what remains is 5x squared minus 4. And we've seen this process for factoring by grouping before in our quadratics section. So if you need some more practice or want to go look at more examples of factoring by grouping, you can definitely go back and look at the videos from that previous lesson. All right, so now we're going to identify zeros and multiplicities of zeros. Zeros of a function are the same as the x-intercepts. So it's where your function hits the x-axis. To find them, we solve the function f of x equals 0. If we are able to factor our polynomial out into smaller factors, we could set each factor equal to 0 to find each of our zeros. So that's why factoring on these is going to be super important. For number 7, we determine the zeros of the function. We need to determine the zeros of the function defined by f of x equals x to the third minus 5x squared minus 16x plus 80. Now, anytime I have 4 terms like that, my gut instinct is going to be I want to factor by grouping if possible. So what I'm going to do is I'm going to look for groups that will give me the same binomial that I can then factor out. So if I look at these, can I factor out a big chunk from each of these kind of grouped together. So from x to the third minus 5x squared, I can actually factor out an x squared. And what remains will be an x minus 5. On the second part, the negative 16x plus 80, I can factor out a negative 16 because negative 16 goes into negative 16 and negative 16 will go into positive 80. When I do that, I end up getting x minus 5 as my remaining factor. So, because of that, I now have an x minus 5 I can factor out, x minus 5, and I can say we can multiply that times what remains here, x squared minus 16. So to find the zeros of this function, I'm going to set this function equal to 0. Well, this function is going to be equal to 0 if either of these factors are equal to 0. Because if this equals 0, 0 times anything equals 0. So if x minus 5 equals 0, then this whole thing will equal 0. And if x squared minus 16 equals 0, this whole thing will equal 0. So I solve each of these little side zero, I'm going to call them zero finders. That's like not an official term, but we can think of it as a zero finder. I'm going to add 5 to both sides here. So we get one factor, or 1 0 is x equals 5. On this one, we're going to add 16 to both sides. So we end up getting x squared equals 16. We take the square root of both sides, but when I do that, I need to make sure I account for both the positive and the negative result on the right-hand side. So we end up getting that x equals positive or negative 4, because the square root of 16 is 4. So the zeros for this function, are x equals 5, x equals 4, and x equals negative 4. Those are the zeros for this function. That's where this function will hit the x-axis. So you could plot those 3 zeros on the x-axis, look at the end behavior, and get a better idea of what your graph would look like. Now, because it's a degree 3 polynomial with a positive leading coefficient, we know that our polynomial will look something like this. And it would hit the x-axis in 3 places, which makes sense because it's a degree 3 polynomial. All right, we're going to look at another example. We're going to determine the zeros of the function defined by g of x equals x to the 4th minus 9x squared. So again, first thing we want to do is we want to factor that. G of x equals, I can pull out an x squared from both of them, which will leave me with x squared minus 9. So to find the zeros, I'm going to take the function and set it equal to 0, which means I need to test each of the factors and set each of the factors equal to 0. X squared equals 0. I'm setting the other factor, x squared minus 9 equals 0. And we're going to solve each of these. Now, taking the square root of this side, I plus or minus both sides when I take that square root, and I get x equals plus or minus 0, which doesn't make sense. It's just equal to 0. Now, on this one, I have x squared minus 9 equals 0, so I'm going to add 9 to both sides. So I get x squared equals 9. Take the square root of both sides. Take the plus or minus. Anytime we take that square root, we need the positive and negative answer. The only exception is 0 because it doesn't have a sign. And I end up getting that x equals plus or minus 3. Now, this is where we need to discuss multiplicities, because this is a quartic function. The degree is 4. It has 4 zeros. The multiplicity of the x equals 0 would be a multiplicity of 2, which we're going to look at below. So the zeros for this function are x equals 0, and x equals 3, and x equals negative 3. And then we'll look at what it means for the multiplicity of 0 to being 2. We'll look at that later. Number 9, determine the zeros of the function defined by h of x equals 3 times x plus 5 times x plus 2 squared. This one is nice because it is already factored out, so it's already got that first step taken care of for us. The second part of this would be to set each of those factors equal to 0. Okay, so 3 can never equal 0, so we don't have to look at that factor, but we got to set x plus 5 equals 0. And we got to look at x plus 2 squared equals 0. So subtract 5 from both sides. On this one, we get x equals negative 5 as one of our zeros. And then here we would take the square root of both sides. Remember, plus or minus 0. 0 doesn't have a sign, so we'd just be left with x plus 2 equals 0. Subtract 2 from both sides. We get x equals negative 2. So those are our zeros for this function. We have this part where we discuss the multiplicity. So if a polynomial function has a factor x minus c that appears exactly k times, then c is a zero of multiplicity k. So what that means here is that in this example, when x plus 2 is squared, that means that x plus 2 shows up twice, so it has a multiplicity of 2. So here we go. For number 10, we're going to determine the zeros and their multiplicities for the function f of x equals 8x times x minus 1 squared times x plus 3 to the third power. So we're going to take, it's already factored out, which is nice. So we're going to take each of those factors and set them equal to 0. And honestly, I can ignore the square and the cube here because we know if I take the square root of 0, it's 0. If I take the cube root of 0, it's 0. So I'm just going to take the x minus 1, set that equal to 0. And then I'm going to set the x plus 3 equal to 0. So divide both sides by 8 on this one. We get x equals 0. Add 1 to both sides on this one, and I get x equals positive 1. Subtract 3 from both sides on this one to solve for x, and I get x equals negative 3. So here are our 3 zeros. The multiplicity of this first one, you could say k equals 1, because that one only showed up once with the power of 1. On this one, the multiplicity is equal to 2 because of the exponent 2 there. And on this one, the multiplicity of x equals negative 3 is 3 because of the exponent there. Okay, now this is why the multiplicities are important. If c is a 0 and it has an odd multiplicity, then the graph crosses the x-axis at c. If c is a 0 of even multiplicity, then the graph touches the x-axis at c. So it doesn't cross it, it like touches it. It almost like kisses the x-axis and then bounces back. Okay, so if we have an even multiplicity, the graph just touches the x-axis at that value. If we have an odd multiplicity, it actually crosses through the x-axis at that value. All right, so given f of x equals negative 3x squared times x plus 4 times x minus 7 to the third, identify the zeros of the function and whether there is a cross point or a touch point at each zero. So it's already factored out, which is nice. We're going to take each of those factors and set them equal to 0. We're then going to look at each of their multiplicities. And then we're going to determine if it's a touch point or a cross point. Solving this one, we're going to divide both sides by -3, which gives us x squared equals 0. Take the square root, we get x equals 0. The multiplicity on this one is equal to 2, and that makes this a touch point. The next one, subtract 4 from both sides, we get x equals -4. The multiplicity on this one is the exponent on that factor right there, which is an assumed 1. So my multiplicity is 1. And so this, therefore, that's odd. So this is a cross point where the graph will actually cross through the x-axis. This last one, add 7 to both sides. You get x equals 7. The multiplicity on this one is equal to 3, which is odd. So this is a cross point. I'm going to start abbreviating touch point with a TP, not toilet paper, touch point. And I'm going to abbreviate cross point by CP. Okay, just for when I'm writing it. All right, so now that we've done all this work, we can sketch graphs of polynomial functions. So we're going to graph polynomial functions defined by y equals f of x. The first step is to determine the end behavior using the degree and the leading coefficient, because you want to have an idea of what it looks like. Is it going to look like this? It's going to look like this. Is it going to look like this? And remember, there could be bumps in between. Is it going to look like this? Okay, that gives us an idea. We would then want to determine the y-intercept by evaluating f of 0. Because once you find one point on the y-axis for that y-intercept, it makes things a little bit easier. Then you determine the zeros, which are the x-intercepts of the function and their multiplicities. Because then you're going to know whether or not your function is going to cross over the x-axis at that point or go through the x-axis at that point. And then you'll draw a sketch starting from the left end behavior. You'll connect the x and y-intercepts in the order that they appear from left to right. Remember, cross the x-axis if the 0 has an odd multiplicity, touch but not cross if the 0 has an even multiplicity. You could think of it as getting like a bounce back, like it hits that 0 and then bounces back on the side that it's on. So let's do this first one. We're going to sketch this function. It's already nicely factored for us, which is really nice. Okay, we're going to determine the end behavior. So we want to look and figure out what's the degree and what's the leading coefficient. The degree is, we're going to add the exponents on each of these factors. Remember, if nothing's there, it's a 1. So 2 plus 1 plus 1 is 4. The leading coefficient is going to be the coefficient of each of these x terms multiplied together. So 1 times 1 times 1, the leading coefficient is 1. That means we have an even polynomial with a leading coefficient that is positive. That tells us that this is going to look something like a parabola with some bumps in between. The end behavior is going to be rising both on the left-hand side and on the right-hand side of the function. Step number 2, looking back, we see that step number 2 is to find the y-intercept. So we're going to go ahead and evaluate f of 0. So we're going to replace all of our x's in our function with zeros. So 0 minus 1 squared, 0 plus 3, 0 minus 4. So that gives us -1 squared times 3 times -4. -1 squared is +1 times 3 times -4. That equals -12. So our beautiful y-intercept is not even on our graph, but we can draw it in. F of 0 is -12. So on the y-axis, it's going to hit at -12 which we'll put a red dot right there. Beautiful. Now we find the zeros of the function. So those are going to be our x-intercepts. So our zeros, we do that by taking each of the factors that we have and setting them equal to 0. So we're going to take x minus 1 equals 0, x plus 3 equals 0, and x minus 4 equals 0. Solve each of these for x. We get x equals 1. Subtract 3 from both sides, we get x equals negative 3. Add 4 to both sides, we get x equals 4. The multiplicity on the first one is 2, so this is a touch point. The multiplicity on this one is 1, so that's a cross point. The multiplicity on this one, where x equals 4, is 1, and so this is a cross point. Okay, so now we have that information. We have now 4 points on our graph, and we're going to go ahead and plot them. So let me plot those zeros. We have x equals 1. We have x equals negative 3. And we have x equals positive 4. We know that the negative 3, which I'm now going to do in purple, is a cross point. And the positive 4 is a cross point, but the positive 1 is a touch point. We know the end behavior, this should be rising from negative 3 upwards. So I'm going to go ahead and graph this in like a light gray so you can kind of see where I'm thinking. So I'm going to start from this furthest point to the left, that we found, which is negative 3. And we know since the end behavior is telling us it's going to rise on the left, we go ahead and draw that arrow pointing upwards towards the left. We then dip down and we go all the way down to our y-intercept. We hit that because we need to bounce back to hit this x equals 1. Now this is a touch point, so it's going to touch and bounce back down. But then we got to flip back around to hit back and cross through that point on the x-axis 4. So we've hit all of our points. Our end behavior matches the way it's supposed to look, rising on both the left and the right. We have a cross point, a touch point, and a cross point, just like we have, and we have our y-intercept. That is beautiful. It is not perfect. We don't know exactly where this is going to turn back around. We don't know how deep it's going to go. So just keep that in mind. This is not a perfect drawing. This is a sketch. I'm going to do one more, and then if there's one more that you can do for practice. If you want to send it to me to check it, I can check it for you. But we're going to go ahead and sketch this one. On this one, we want to look at our degree and our leading coefficient. The degree is 3. The leading coefficient is a negative 1. Okay, so we have an odd and we have a negative leading coefficient. So that means it's going to look something like boom, boom, boom. Okay, now, so we know it's going to rise on the left and fall on the right. We're going to solve for our y-intercept. So we're going to find f of 0. That's going to be negative 0 plus 1 times 0 plus minus 3 squared. So that's going to be negative 1 times negative 3 squared, which gives us negative 1 times 9, which is negative 9. So our y-intercept is negative 9. We're going to find our zeros by setting each of our factors equal to 0. So x minus 1 equals 0. X plus 1 equals 0. X minus 3 equals 0. I take the factor exactly as it is. I'm going to solve each equation for x to find those x values. X equals -1, x equals 3. The multiplicity on the first one is 1, so it is a cross point. The multiplicity on x equals 3 is 2. That is even, so that is a touch point. So I'm going to plot those x-intercepts. We have x equals -1 and x equals +3. Looking at our end behavior, it should be rising on the left, and so therefore I'm going to have, from this point, I'm going to have it going upwards. It's going to dip down and cross through -1 because -1 is a cross point, all the way down to our y-intercept. It's going to come back, bounce and kiss and touch at +3, bounce back down, and falls on the right. So this is how we get sketches of these polynomial functions. Again, if you want to try the last one, send me a picture of it and I'll tell you whether you got it right or not, or a good sketch of it. That sounds awesome. If you have any questions, email me and let me know. Thank you.